Diodes are pretty cool things. They allow non-linear behavior, which kind of associate with things like distortion characteristics. They can do a lot more than that. They can clamp voltages, so we can use them for voltage regulators. So you can put them in your stomp boxes to stop people applying 12 volts instead of 9 volts and things like that. So yeah, we're going to look at how they work, and hopefully at the end of this you'll be able to understand the operation fully and to build some neat little circuits with them. One of those neat little circuits that you might want to build is this, which is a Tubescreamer. Pretty easy thing to build, and it relies on back-to-back diodes and the fact that these diodes exhibit different characteristics whether you apply a voltage, what we call forward bias or reverse bias, across them. And what do we mean by that? We'll explore that in this presentation. So a diode in the first instance is effectively doped silicon, and it's doped to basically increase its conductivity. But when we dope the silicon, we end up with two regions, a P region and an N region, and this is why often you hear things referred to as a PN junction or a PN diode. So with the P region, we often refer to this as the anode, and the N region we refer to this as the cathode. And it's these 2 points that determine how the diode's going to operate when we connect it to a power supply. When this voltage here, the anode voltage, is bigger than the cathode voltage, then we often say that the voltage, the diode itself, is forward biased. If it's the other way around, we say that it's negative biased or reverse biased. And what this means is, if this voltage at this point is smaller than the voltage at this point, then you will get effectively no current flow through this diode. So it will just sit and do nothing. However, when the voltage here is much larger than this voltage here, we get current flow in this direction. So obviously, if you think about that, you can use this to stop current flowing in this direction, and we can allow current flow in this direction, which is a pretty cool thing. And if the diode symbol itself, you'll see, is kind of like an arrow, so this kind of reminds you of the general flow of what we call the forward bias region, or the forward bias operation. Up to the point when these electrons can happily flow during forward bias, as you can see here, on this plot, what we can see is this is the forward bias current, and this is the voltage, the forward voltage that's applied across the diode. What we mean by that, if I draw a diode here, make that positive and that negative, the voltage there is what's known as the forward voltage. Now, if you look at this plot, we've got 0.1, 0.2, 0.3, 0.4, up to the point of around 0.7, 0.65 volts, virtually no current flows. So at that point, what's happening is the depletion layer is still a little bit too wide for current flow to occur. But as we get around this 0.6 volts, 0.7 volts, so if I make this 0.65, 0.7, this depletion layer becomes much smaller, and we get this inrush of current. We get this current that's able to flow now through the diode, and we call this the forward bias region. So anything above 0.65, 0.7 volts, we are actively enabling the diode to function, and we get the current to flow. Whereas below that, we basically, this is called leakage current. We're not allowing the diode to do anything. Now this varies for germanium or silicon. We see that this voltage changes for different diode types. Now there is a diode called a Zener diode. We specify a breakdown voltage which specifies at what point this Zener diode is going to conduct in its reverse bias mode. So what can we do with these cool curves? You'll see now this is the this is when the diode isn't conducting. This is when it begins to conduct. We get these nice curves. Now what do these curves look like? Well, they look a lot like compression curves, and we can utilize these diode characteristics for clipping or building sort of fundamental, very basic compression systems, which is why they're such useful components.